This is the fourth lecture in Unit 5, and this lecture is about how the electron configurations and the atomic structure, nuclear charge, etc., affect the patterns that we see on the periodic table. So this is about periodic trends. Please make sure that you have set up the learning targets and looked up the vocabulary and kind of looked for the patterns before you watch this lecture. I'm going to give you some bare bones in what's happening here, but it definitely will not be as easy to do for you if you don't have this set up first. So when you're finished, then you can restart the video. Okay, so the first thing that you have to remember about everything that's a pattern on the periodic table is that it's based on several different things related to atomic structure. So the trends that we're going to talk about today are all based on basically a few separate things. And so the big one that does a lot of, gives us a lot of information about the attraction of the electrons to the nucleus, which is largely what these patterns describe, is the energy level in which the electrons are found, which tells us the basic distance from the nucleus. So remember that Coulomb's law tells us that the charge and energy are directly proportional, that the greater the charges, the positive and negative charges, the greater the attraction, and that the distance and the energy or the force of attraction are inversely proportional, that the farther away those two charges are, the positives and negatives are from each other, the less attracted they are to each other. So when we're talking about energy level as distance from the nucleus, this is definitely a big piece of Coulomb's law and the force of attraction between them. So that's first. We also have something called shielding, which is like pieces of paper getting in the way of a magnet holding your paper to the refrigerator. So the more inner electrons you have between those outer electrons, because typically we're describing the attraction of the outermost electrons. So the more inner electrons there are, the more core electrons there are, the more that positive charge from the nucleus, that positive field from the nucleus is, it's not really sucked up, but is blocked by or shielded by the electrons in the center. So the shielding would actually lessen the force of attraction, the more shielding there is. And this becomes really important as you go down groups, as you're talking about adding an energy level, because not only are they farther apart from the nucleus, but they're also shielded from the nucleus. And then finally, the effective nuclear charge is based on the number of protons in the nucleus. And so as you add protons to each atom, the charge of the nucleus increases. This, of course, increases the force of attraction. So we're basing all of our patterns on the periodic table about these three things. And so it's really important that you always have these in mind. So the first one I want to talk about with you is atomic radius. And this is described as the distance between the nuclei of two atoms that are side by side, right? And usually it's half the distance if we're talking about two atoms that are identical, like here, where they're both chlorines, then half the distance would be the nucleus. Whereas once we know the radius of one atom, then we could subtract to find the radius of another in something like this. In metallic substances, it's half the distance between nuclei of adjacent atoms. So basically, we're talking about the size of the atom. And you should picture then that as we increase atomic number, as we're going down a group, that the atomic radius increases. And the main reason for this, of course, is that you're adding an energy level and the electrons are getting farther away from the nucleus, so the force of attraction is lessened. The second reason is that there's also shielding, which would be the inner electrons shielding the nuclear pull from the outer electrons. So both of those reasons give us a larger atomic radius as we go down a group. As we go from left to right in a period, so as atomic number increases within a period, atomic radius decreases. This would be because the nuclear charge is growing, but the basic distance from the nucleus is staying the same. Remember, you're not increasing shielding, and as you go across a period, those electrons are all being placed into the same energy level. The second energy level or the third energy level. So they're the same basic distance from the nucleus. And if the nucleus didn't gain a proton, then probably the repulsion between the electrons there in the electron cloud would actually have the atom growing. But because of an increased number of protons in the nucleus, now the atom shrinks. So this is an important pattern for us to watch. And then finally, what we see is that within the transition metals, so up here I was talking about main group elements, basically the S's and the P's, and you can see that pattern pretty clearly. Within the transition metals, it's not quite as the same. It's not as consistent. It definitely is getting smaller as you go from left to right. But you have to remember that the size of the atom is determined by the outermost electrons, and these electrons that you're adding here are all inner electrons. So what's happening is even though you're adding a proton and it should be able to pull in those outer electrons, so remember, like if we're here, we're adding 3d electrons, but these 4s electrons are the edge of the atom. So what's happening is as we're keep adding these electrons, we're adding a proton which should be able to pull these guys in farther. But because we're adding these electrons in the middle, it's actually increasing the shielding. So what we see is that across the transition metals, it doesn't shrink as much as it does across main group elements because of the increased shielding every time you add one of those electrons. So these patterns are really important to understand. You can memorize them, but you're going to have to explain them. You're going to have to think through them. Often what will happen is that they might give you a statement of this atom is larger than this one, explain, or this atom is smaller than this one, explain, and sometimes it's something that you're not really expecting. So you have to really understand the patterns so that you're able to discuss them. Okay, so that's the first pattern that we wanted to discuss. Atomic radius is largely the reason for most of our other patterns, and it happens to be inversely related to most of our other patterns. So if you can remember that the largest atom is in the lower left-hand corner of the periodic table, and the smallest atom is in the upper right-hand corner, then that will help you make your decisions, and then you can think about how to explain them. All right, so ionization energy, typically we talk about first ionization energy most often. It is the amount of energy required to remove 1 mole of electrons from 1 mole of atoms in their gaseous state. So basically we're putting in enough energy to excite an electron all the way out of the atom. And it would be out of the, it's like basically the last electron that we put in. Okay, so it's usually from the valence shell. We don't often talk about it for transition metals just because it's not a very consistent pattern for transition metals. So usually we're talking about the valence shell. The second ionization energy would be after we remove 1 electron, let's remove another. And how much energy would it take to remove that? The third ionization energy would be after we've removed 2, let's remove a third. And how much energy would it take to remove that electron? So successively, they always get higher because you have fewer electrons, but your protons aren't changing. So the effective pull of the protons on the electrons gets better because there are fewer electrons to be pulled, and so the field pull is stronger per electron, if you want to think of it that way, and it can kind of pull them in tighter. What we notice is that in second ionization energies, you can always see after looking at, successive ionization energies, you can always see where the next energy level would begin. So I want you to see that if we're talking about lithium, its first ionization energy, and this actually looks like the binding energy that we saw in those PES spectrum of that last electron. So this would be for the 1s, let me do it this way. This would be for the 2s1 electron, right? Notice that if I'm going to come in and pull out the 1s2 electron, that it takes a lot more energy. That would be because we're pulling it from the core and it's much closer to the nucleus. We can do the same thing with beryllium, and we can say, notice that in beryllium, this would be the 2s2 electron, this would be the 2s1 electron. So yes, it's more difficult, but not dramatically so. This would be the 1s2 electron. that you're trying to remove. So notice that it's a humongous difference. So you can follow this pattern and keep going. And this for boron would be the 2p1 electron, and then the 2s2 electron, and then the 2s1 electron. And now we're in the first energy level. So if you're asked to tell like how many valence electrons something has by using successive ionization energies, look for that really big difference. And then what you know is that this is an inner or core energy level, okay? And so the one before it would be the last of the valence electrons. So basically all of these would be valence, and then the core electrons would be after the great big jump. So this is just kind of a way to think about how to interpret that. We'll practice those in questions. The next thing that I want to talk about then is the overall pattern. First ionization energy, remember, removing only one electron. Overall, the pattern is that as you go down a group, the atomic number increases within a group. The first ionization energy decreases. This is not a perfect pattern, but for the most part, we see that as you go down a group, it gets easier to remove that electron. This is largely because the electron is far from the nucleus in a higher energy level, and there's increased shielding. As you go across a period from left to right, you can see that for the most part, it increases as you come across the period. There are some exceptions, and I want you to picture those PES graphs, because what we're looking at is that without the extra shielding in periods 2 and 3, when we add the p electron, that p electron is a little bit farther from the nucleus. It doesn't penetrate the nucleus quite as far. And so that last electron, like in boron, is slightly easier to remove, or in aluminum is slightly easier to remove than the 2s2 electron. But that quickly is overridden when you keep looking, and it continues to increase. Remember, though, that we talked about when you add the second electron into your p orbitals and they have to share, now we have repulsion and it decreases again. So these are for two different reasons. Between group 2 and 3a, between boron and beryllium, or magnesium and aluminum, then what we're talking about is the idea that this is because the p electrons, we call it penetrate the nucleus less, because those orbitals are slightly elongated and they're just not as close to the nucleus, so they're just not as attracted. And so the first one to remove it is simpler. Once it's there, now you add a proton, and your comparison is to the same basic idea with an extra proton, so the ionization energy increases. Between groups 5 and 6a, it's going to decrease because of increased repulsion, because electrons are sharing orbitals, an orbital. Okay, so remember though, those two reasons are different, but you see those two little bumps or glitches in that overall increase across a period. Electron affinity is a difficult concept. It's kind of the idea that it's the change in energy. It could be positive or negative if we're going to add an electron. So it's like the opposite of ionization energy, where we're adding energy to remove an electron. Now it's the change in energy if we add one. For the most part, most EAs are negative. Okay, by adding one electron, mostly it's an exothermic process. It's a lower energy state. It's the attraction to the nucleus is pretty easy to occur. So for most things, adding the first electron is exothermic. The noble gases, of course, it's almost very difficult to add an electron. You have to force it into a new energy level, and so this is the exception. In general, the more negative the electron affinity, the more likelihood that you will gain an electron. So things with high ionization energies have more negative electron affinities, a bigger value, more negative, right? Or a bigger number, but more negative. So the really reactive nonmetals like the halogens and the oxygen group have very negative electron affinities, and they make anions. The cations that are formed from the metals are because their electron affinities are just barely negative, and so they're overall less likely to gain electrons, more likely likely to lose electrons, and they form cations. And the noble gases, of course, with their positive EAs don't usually bond at all. So you can kind of see now that we've added these patterns, and you can see that in general, remember these are generalizations, not specific patterns, but in general, atomic radius and the ionization energy and electron affinity are opposite of each other. All right. The next thing that I want to talk about is electronegativity, and this kind of is a combination of all these ideas because it's the relative ability of a bonded atom to attract electrons to itself. So it's important in bonding. It helps us to make our decisions as to whether the bond will be ionic or covalent. It helps us to make decisions as to whether the electrons will be shared equally in a covalent bond or unequally in a covalent bond, etc. Unlike the other patterns that we've seen in electron affinity and ionization energy, electronegativity is a comparative value. Your book talks about how they relate together, the energies of the bond versus etc. But it's not important that you understand that piece. What I do want you to see is that it mostly matches the pattern of first ionization energy. And so we want to consider that. It is a scale created by Linus Pauling where 4O is the best and fluorine is on the Pauling scale an electronegativity of 4.0. Hydrogen is not shown in this graph, but you notice down here that hydrogen is actually a relatively high electronegativity. This is because it's a nonmetal. So the pattern being the nonmetals have higher electronegativities, are more likely to attract the electrons toward them in bonding, and the nonmetals have lower electronegativities, so they're less likely to attract the electrons. And most noble gases are not assigned electronegativities, but boron and krypton actually will bond, especially with the halogens, and so some charts include them in electronegativity values. Of course, they would be somewhere in here, and they're similar to, not, but lower than the bromine and the iodine, mainly because of the fact that their energy levels are full. So just kind of keep that in mind. Electronegativity is, of course, going to follow the same reasons. Across a period, electronegativity increases because of the increased pull of the effective pull of the nucleus. And down a group, it decreases because of the distance between the electrons that have been bonded, or where those electrons that bond would go, and the nucleus. So the physical distance in Coulomb's law, as well as the shielding. Let's see. When we do bond type, we'll talk about how you can predict which type of bond based on electronegativities. One last thing I want to talk about here is a trend in metallic behavior. So I want you to picture that metallic behavior means losing electrons. And the more easily you lose electrons, the more metallic you would be. So you're going to lose your electrons more easily if your electrons are in a very far energy level from the nucleus. So francium on our periodic table would be the easiest to lose electrons. Compared to the other elements that have electrons in that same energy level, francium has the fewest number of protons. That energy level is really far from the nucleus, so the effective pull of the protons is weak, and there are lots of core electrons shielding it from the pull of the nucleus, and so it's pretty easy for francium to lose an electron. What you'll notice is that within the metals, our metallic behavior increases in that direction, more likely to lose electrons because they are less electronegative, they have lower first ionization energies and less negative electron affinities, etc. The nonmetals, of course, have less metallic behavior, and it would decrease, basically, so it's going to increase the same, but we want to picture that this would be, in the upper right-hand corner, the most non-metallic. So it's kind of weird. You have to be careful if you're comparing groups over here when you cross the line. You have to be super careful about what you're talking about there, but you just want to kind of keep that straight. So we'll do a lot of practice. It's really important that you understand the reasons. So focus on the reasons instead of in first year where you might have memorized the patterns. Now I want you to focus on the reasons and focus a little bit on the exceptions that occur, focus on how they fit together, etc., and we'll practice this in class. Thank you.